All right, I'm going to do this problem without noting what number it is, nor saying what test it came from, because I'm going to break the habit of saying that at the start of every video. What's going on this time is we have a bounded subset of the real line. So just think a set of numbers that doesn't go off to infinity. Right, there exists some number that every number in this subset is less than or equal to, and there exists some other number so that every number in this subset is greater than or equal to. It's connected, and it has more than one point. So now we're thinking that it's an interval. So like, I don't know, A to B, maybe it includes the endpoints, maybe it doesn't, and it has more than one point. Okay, cool, so A doesn't equal B. So I guess what we know from these different statements, we could summarize a little bit loosely speaking with something like this. Now we're going to consider some function f, and importantly, it's a continuous real valued function defined on this set S. And what we're asked is which of the following statements must be true? The first statement says that S is a closed interval. No, might be an open interval, right? Because it's connected, it's an interval. Because it has more than one point, it's not the closed interval from 4 to 4, for example. Because it's bounded, neither of the endpoints are infinity, but nothing in here says that it has to be closed. This is a false statement. For example, we could say S is equal to the open interval from 0 to 1, maybe. Is that bounded? Absolutely it is. It's bounded below by 0 and above by 1. Is it connected? Sure is. Does it contain more than one point? Absolutely. 1/2 and 1/3 are both in here. Statement 1 is certainly false. What about statement 2? The set f of S has a maximum value. Well, this is also a false statement. To show that it's false, I need to figure out what my function f should be. You might notice that this set right here, S, does not have a maximum value, right? Because if I ask you what the maximum value is, you might think 1, but it's not 1 because 1's not included in this set. And you're like, right, but the question's not about S having a maximum value. It's about f of S having a maximum value. Okay, what if we consider the function f of x equals x, right? The identity function. It would map this open interval onto itself. F of S would be the open interval from 0 to 1, as we already talked about. This does not have a maximum value. Right? You might think it's 0.999, but I'd argue 0.99999 is bigger than that number. This is a false statement. And there's really nothing special about this function. Lots of functions would work in this place. Really, the key idea is that we're mapping an open interval to an open interval. So we have two false statements. Is that enough to answer the question? No, of course not. We know the answer is not C or D or E, but at this point, we're not sure whether it's A or B. To figure out whether it's A or B, we need to evaluate the validity of this last statement. The set f of S has a least upper bound. Well, in this case, the set f of S had a least upper bound, right? The number 1 would work. It's an upper bound because every number in this set is less than 1, and it's a least upper bound because you can't come up with a number less than 1 that's greater than every number in this set. So in this specific instance, f of S does have a least upper bound, but in order for this statement to be true, that must be true for any set S satisfying the criteria in red and any function f satisfying the criteria in blue. So can I come up with an S and an F to produce a set that does not have a least upper bound? Well, an easy way to get it to not have a least upper bound is for my set to map onto an interval whose right endpoint is infinity. I guess I should have put plus or minuses here. I guess I should have put plus or minuses in here or whatever. So how can I do that? Well, one example would be to let f of x be equal to 1 over x. In fact, if I choose this function, I can choose the same set S that I've kind of picked on already. If you take this bounded, connected subset of the real line that contains more than one point, and you map it onto some subset of the reals using this function, which is definitely continuous on this interval, and it's defined everywhere on this interval, the image of this set under this function would be the open interval from 1 to infinity. Right, when I plug in numbers from this set that are arbitrarily close to 1 divided by something that's arbitrarily close to 1 gets arbitrarily close to 1. And when I plug in numbers from this set arbitrarily close to 0, 1 divided by a number that's getting close to 0 goes off towards infinity. This definitely does not contain a least upper bound. Statement 3 is false. All 3 statements are false. It looks like the answer to this question is A. If you were able to get this question correct, or at least you follow the logic in these solutions, it might make you feel good to know that only 37% of test takers got this question correct.